Hello everyone, and welcome to session number 9 of this set of videos created to explore programming applications in reinforced concrete. In this session, I will be using Maple, and I will present a Maple document that is capable of designing singly reinforced rectangular concrete beam cross-sections. But before we begin, I would like to draw your attention to the importance of the word design for engineers. Inherent in the word design are the words safety, economy, and serviceability. A design objective could be to minimize cost while ensuring safety and serviceability, maximize safety in an economic serviceable framework, or to obtain the most economic safe design while maintaining long-run serviceability. Design is not to be taken lightly by an engineer. The designed cross-section should always be investigated in order to make sure that all the assumptions made during the design process are actually satisfied by the final designed cross-section. Every design should be followed by an analysis to make sure that the design was thorough and that the assumptions made during design were actually true and, if not, corrected. The Maple document that I will show you in a minute performs the required design procedure, produces the required number of design alternatives, checks these design alternatives with full cycles of analysis to make sure that the design alternatives satisfy all the code requirements, and then chooses the best alternative based on a predefined set of selection rules that guarantee best performance. This is the Maple document that I am talking about. It is developed for the design of singly reinforced rectangular beam for flexure. These here are the parameters that the user needs to insert for the document to function properly. The first one is the required factored moment, the moment for which the cross-section is to be designed. Initially assumed diameter of bar, yield stress of flexural steel, compressive strength of concrete, concrete cover, diameter of stirrup, and then the range of rebars to be used in the design process. The next factor is a design economy factor, which provides an additional safety buffer zone for the design process. It is equal to the design strength divided by the factored strength and presented as a percentage. So 1.1 here means that the design strength can exceed the factored moment up to 10%. Next, and in order to calculate the depth of the beam, the user has two alternatives. The user can insert a given value for the depth of the beam. In many cases in design, the depth would be given or restricted by the architect or for any other reason. And if the depth of the beam is not known and is to be designed by the Maple document, then the user leaves h given here as 0, and the document will calculate the depth of the beam. To calculate the depth of the beam, the document needs two pieces of information. The first piece is the length of the beam center to center, and the second is the support conditions for the beam. If you check the second figure on the right side, you can see that we have 4 cases for the support conditions for the beam. According to the ACI code, the span that you are looking at can be simply supported. It can be one end continuous, both ends continuous, and the beam could be a cantilever. The user specifies which support condition is to be used by determining a numerical value for the parameter ident support conditions. It can take the values 1, 2, 3, and 4. Now, to determine the width of the beam, the user can either insert a given value for the width of the beam. In such cases, the width will be predefined, and if the user does not know the value of the width of the beam, then the user can insert 0, and the document will consider b to be equal to h over 2. For the first example that we will run here, We are considering a required factored moment of 300. Initially assume diameter of bar 25 millimeters, 420 yield stress and 30 megapascals for the compressive strength of concrete, 40 millimeters cover of concrete, 10 millimeters as the diameter of the stirrup. We are requesting 9 different design alternatives. Each design alternative will be composed of one of the bar diameters shown here in this array, from 12 up to 30 millimeter diameter bars. The range for economy is 1.1. We are not specifying a value for H so that the document will calculate the depth of the beam based on the given beam length center to center, and the supports condition here are chosen to be one end continuous for the span under consideration. This means that the span that we are studying is one end continuous, and the length of that span from center to center is 11 meters, 0.9. The width is not given, so that the template will calculate the width of the beam. Let's run the first example here and check the output. Here you can see that the depth is calculated based on span length and support conditions. The total depth is taken as 650 millimeters. The width is taken as half that and corrected to be 350 millimeters. This here is the design alternatives matrix. It shows 9 different design alternatives. Then a section is chosen based on a predefined set of governing rules. The Maple document plots the cross-section and shows the ductility status of the beam. Let's change some of the input parameters and see what happens. I'm gonna change here the support conditions for the beam from one end continuous to both ends continuous, and leave all the other parameters as is and run the Maple document. We can see here that the first 2 bar diameters are now rejected. They did not satisfy the conditions of the ACI code. Here we are assuming that the steel will be in 2 layers only in this document. The section is chosen based on a predefined set of rules. And here we have a plot of the cross-section and of the ductility status of the beam. Let's go back to the input parameter zone and change the required moment from 300 to 350 kilonewton meters and run the Maple document. We can see here we have the design alternatives. This here is the chosen section. This here is a plot of the cross-section, the design cross-section, and its ductility status. Let's increase the required moment from 350 to 400 kilonewton meters. Check what happens. 3 sections are rejected. This here is the chosen section with its figure and ductility status. I'm gonna change the value here to 550 kilonewton meter and click run. You can see here that all the alternative design sections are rejected because the steel could not be arranged properly in 2 layers, or the section does not satisfy the ACI code requirements in terms of the strength reduction factor phi, where we can see here that the strength reduction factor phi is less than 0.9 and thus the section is not tension controlled. Let's go back to the input parameter zone, change the moment back to 300, and this time remove 12, 14 and 16 millimeters from the range of design and run the document. We can see here that the design alternative matrix now has lesser number of design sections because we reduced the number of bar diameters to be considered. This here is the chosen section, its plot and ductility status. Let's go back here and try something different. I'm going to return the bar diameters, 12, 14, 16 and 18, but this time I'm going to specify a value for the depth of the beam as 650. Let's run it and see. You can see here that now H is specified by the user. These here are the design alternatives. This here is the chosen cross-section, and these are the associated figures. We can also go back and insert a given value for the width of the beam as 350 and run the code. We can see here that h is specified by the user and the width of beam is also specified by the user. Here we have again 9 different alternatives. This here is the chosen section with its figure and ductility stats. This concludes this session. Thank you very much for being with me, and hopefully I will see you in the upcoming sessions. Best wishes.